Hey guys, it's me again, and I'm out here with another video talking about operators. Now, first off, we're going to start off with this postulate 2. I forgot to mention how postulates work. They're basically the rules of quantum mechanics and wave function and all that stuff. So let's talk about postulate 2. Postulate 2 states that any physical observable can be measured with operators. So I'll just write that down. Can be measured with operators. As I mentioned in the last videos, these include stuff like position and energy. And what operators are these things that operate on wave functions to give these physical observables. I'll give you an example of an operator, which would be the derivative operator. Now, when you apply this to the function, it takes the derivative of that function. And what this does, it does, let me give an example, d over dx. So if I were to operate this on a function like f of x, then this would give you the derivative. And that's what it does. Basically the operation onto the function. And the thing about operators, you can apply two operators on something. So let's just say we have an arbitrary operator, operator A, and operator B, and it would operate on f of x. What what we have to note is B is on f first. So B would operate first. B operates first. Oh wait, operates first. Then A. So the operator to the most right or to the most right will operate first, or basically the operator that's closest to the function uh, operates sooner. So knowing that, let's just talk about what linear and Hermitian operators. So first off, what a linear operator is. So let's just say you can apply an operator to each function. Let me just say can operate. Oh, we can apply operator. Can apply operator to each function. So let's say we have an arbitrary operator omega, and this operates onto f of x plus g of x. And this were to operate on this here, this would give you, it's basically saying that this is true. It is equal to if the operator was applied separately. So an example of a operator would be, let's say, the position operator x. If I were to operate x on this on f and g, you can put that in and you can simplify it, and then this will give you this on each function. All right, now let's talk about Hermitian operators. And Hermitian operators are basically just means it's I'm gonna go more in detail in future videos, but all you need to know now is that it doesn't matter which, like if you were to do an integral over all space and you were to apply an operator onto it, so like in this case omega onto g, this is the same as you were to operate on the other function. Uh, so basically, it doesn't matter where to apply the operator. You can apply it to F, you can apply it to G, you'll still get the same answer. Alright, what is next? Alright, as I said, an example formation operator would be X, because basically, if you were to apply X here, you would it'll just be F times X times G, and that would just be and it'll be the same if you were to operate on F, because it'll just be X times F times G. So, and another example would be, but that's an example of a Hermitian operator. Now let me show you an example of other operators. So let's just get an example of another operator. This is called the linear momentum operator. And this is just the imaginary number times h bar times the derivative operator. And this is I'll say linear momentum operator. So if I were to try to find a linear momentum, then I would apply this operator, and it will give me the value of that. And I'm going to discuss. You can only do it in some cases, and in the future, I'm going to tell you. I mean, later on in this video, I'm going to tell you when you can use that. So, that's basically the linear momentum operator, and I'll just say h bar is just Planck's constant over 2 pi. All right, so let's go on to the next value, which would be, the next example of operator would be the energy operator. And if you want the energy of, let's just say, a particle, you just apply it on the wave function, and you have the energy is equal to k plus. So this is what the energy is equal to. If you were to convert this, I'll say kinetic energy and potential energy. This is how you classically find that energy. Now, if you were to put it in terms, let me just put that in between. This is basically 1/2 mvx squared plus, let's just say, v of x. Now, let's just say if you want to convert this into quantum mechanical terms. This is the classical terms right now. And we want to put this into quantum mechanical terms that we understand. So, if we were to convert this, let's just say we want to put this in terms of something we know, like momentum, right? Momentum is equal to 1/2 m times p of x over m squared. Because if you really think about it, momentum is just m times v, and this is equal to p. And if you want the velocity, you can divide m on the other side, and then you would get p of m, which will equal velocity. So you just replace velocity into this. Alright, knowing that, we put this into quantum mechanical terms, and that would be, I'll just put this. This will give you this. Wait, sorry about that, guys. Just give me 1 second. Alright, and this would be I forgot to mention that p of x squared, it just means you operate 2 times. So it's basically saying the same as, let's just say this, p of x, and that's p of x. And we call the energy operator a Hamiltonian operator. This will be h. So to operate, I would just apply h onto a wave function, which will give me the energy. Alright, let's see what else I forgot to mention. Okay. Oh wait, let me also state what this is equal to. It is just negative h bar squared over 2m derivative operator. Because you squared it, you just do the derivative 2 times. So it's the second derivative plus v of x. All right. Now you guys don't need to necessarily learn this week about energy. It's just a good way to get the idea of what operators are. Just put that in the back of your mind. You're gonna use this in the future to do stuff like particle in the box. All right. Oh, I got examples here. Let me add a page. All right. Next, let us see what we can do. All right. So this is just postulate 3. This is another rule. You can get measurements of let's just say arbitrary measurement, of, let's say, this here, like any like position, energy or stuff like that, are eigenvalues W. So measurements done by an operator are eigenvalues. So let me give an example. Let's just say we have an operator here and we operate on a wave function. And if the wave function is maintained, you still get the same wave function. You get this, and this would be the eigenvalue, and this would be an original function is maintained, and then this would be original function maintained. So if it's maintained, this would be an eigenfunction. Oh wait, yeah, eigenfunction. You get the idea. And this is the operator. Now, okay. Now let's see what else. Uh, let's say that we have. Let me just give you guys an example. I'll go to the next. Oh, it's on the next page here. Okay. Now, we're gonna go examples for linear operator. For linear operator. So let's just say, like I told you, it's x to the third. So let's just say I have x to the third, and I operate on two functions, right? This would be the same as if I were to do this. So operate on these separately. This would be the same as that. Oh wait, yeah, without the operator, it's just x to the third times g of x, and this would just be, oh wait, x to the third, which would equal x to the third times that whole function. All right, and this would be linear because I just proved that. Now, the derivative operator too, if we were to do the same thing, okay, we would do that separately, so it would be f prime of x plus g of x. The same as if we were to operate on these separately. You would still get the same answer. So this is also linear. Should I do momentum? So I'm not gonna do momentum, but I'm gonna give you a reason why. Because momentum operator is just a constant I and h bar over derivatives, and this is f of x plus g of x. Now we know that is the derivative is a linear operator. Now if that's true, that means that this whole thing will be linear. And this is just a constant. And multiplying by a constant is linear also. So this is linear just by knowing the fact that the derivative operator is linear, and since it's multiplied by a constant, it's automatically linear. All right. And this is also, I think I pulled this example from your recitation that you guys are gonna do. So this is just an operator called it's nothing you're ever gonna use. It's just like a made up operator. So it's basically saying, oh, whatever if I operate on this, I put whatever function is inside. So if I were to do sine of g of x plus f of x, this is not equal to sine of g of x plus sine of f of x. Because think about it. What this is saying, I operate on this separately. And this is just, I'm operating on g of x separately and sine of x separately. But I operate on this entire thing. This is not equal to it. That's like saying sine of 45 degrees. Oh wait, let's just say sine of 45 degrees plus 45 degrees is, and that's not equal to sine of 45 degrees plus sine of 45 degrees. I'm not saying these are the functions, but it's just an example. This is not equal to each other. So whatever function you're gonna put in there are not gonna be equal. This is means it's not linear. All right. Anything else? Oh, this is eigenfunctions next. All right. So let's go on to another example, which are eigenfunctions. So let's say now I need to find the following functions or eigenfunctions of the following operators. I also supposed to list what are their eigenvalues too. So let's just say, right, we do a little of this. Derivative operator onto e of negative a of x. No, a is just a constant, just to let you know, it's just a constant. So you take a derivative of this, what will this equal to? You know, it's the chain rule, so it's just negative a times e to the negative a of x. Now, this is just a constant times the function, and this is the eigenvalue, because as we saw from the notes, this is just an eigenvalue. I forgot to mention that it's going to be a constant. Okay, eigenvalues are always constant. Alright, and then so this is just a constant times the original function. The original function is still maintained, and so that's the eigenvalue. I mean eigenfunction. Sorry about that. All right, so knowing that fact, this proves that this is an that the e to the negative a of x is an eigenfunction of the derivative operator. Now how about x squared? Now if we use x squared, right, onto f of x, this will give you x squared to e to the negative a of x. Now unfortunately, this is not an eigen e to the a to negative x is not an eigenfunction of the x squared operator. And the reason because of that is because you have the x squared over here, which is not a constant. This is a function of x, and this is basically making this into a new function. So this makes it into a new function. Basically saying that 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 the hypothetical value is changing with x. So this right here is not not a eigenfunction of x squared operator. All right, now let's go on to the next one. Sine of b of x. I think I have this next. Yep. All right, so let's just say we have sine b of x, right? We take the derivative of this. And hopefully you guys know what this is. This is just equal to b, it's b cosine of b of x. You take a derivative of that, and the function changed. It's not sine anymore. So this cannot be a eigenfunction of the derivative operator. All right, now this is not an eigenfunction operator. All right, next part, derivative squared. Okay, so let's just say I take this second derivative of sine of b to the x. Now we know what, now solving this on top, we know this is we operate on this once, so we have one derivative left over. That still needs to do the operation on the function, and this will be cosine of, oh wait, yeah, b cosine, b cosine of b to the x. Now we can still operate on this again because we still have a derivative operator left over. And so operating this again, we get negative, because derivative of cosine is negative sine, negative b squared of sine of b to the x. Now, because it's only a constant times the original function, this is the original function, here, we have, and this is just a constant, I forgot to mention that b is just an arbitrary constant, but this is just a constant, and the constant times a constant is just a constant again. This is going to be the eigenvalue, and this is the eigenfunction of derivative squared. All right, now go to the next part. We have h e to the negative a of x, and we're going to find if this is the eigenfunction of the derivative operator. So let's operate on the hx. All right, operating on h of x, and this is just, oh wait, the intermediate, a to the e to the negative x. And we guys know from the math review that you have to do the product rule because you have x times e to the negative a of x. This would be, let's say, let's try to make them the first taking derivative of x. So let's say derivative of x times e to the x. So you got e to the negative a of x plus, let's see, that, x, oh wait, negative a times e, oh wait, times x, e to the negative a of x. Now, you get this, we'll simplify that, oh wait, minus a ax. Now I try to simplify this because I'm going to try to see if this is an eigenfunction or not, and it's not because of this x here. This is saying this right here makes it that this can't be an eigenvalue. This here can't be an eigenvalue because of that x here. It just makes it into a new function. So this is not an eigenvalue, not an eigenfunction of the derivative operator. All right, I believe that is. Oh wait, let's just one more note before I end it. It's about postulate 4. Saying that the average value of, let's just say, an arbitrary measurement, omega, can be calculated using a normalized wave function. So let's just say I want to make an arbitrary measurement, like the average of overall space, right? So then we would, to get the average value, let's just say I want to calculate the like x, right? I would have to integrate over all space, and multiply the operator. So we do this, the operator, and I mean the wave function, multiplied by the operator, and that's gonna apply to here. And what this does, it repeats the measurement. It repeats the measurement over all space from let's say negative infinity to infinity. It's an example, and then it measures it from each value, and then it averages it. And this is just another way of getting a measurement if we can't find it using the if it's not an eigenfunction. I mean, saying if the wave function is not an eigenfunction of the operator. So let's just say average of replicas. So the replicas would be probably like at negative 100 or something of the system where is recorded, then averaged to obtain. I forgot to mention this is the expectation value. All right, and I forgot, and I also mentioned before that this is just to can be used. It's used for operators that are not aren't let's say aren't eigenfunctions of the used for I'll say wave functions or functions of the operator like x. You guys are gonna learn this in the future and of taking the average expectation value, and it's pretty simple. I have to say, just plug in just plug in like probably like an example would be x and integrate over all space, and then you'll get your expectation value. You guys are gonna also learn about the Heisenberg uncertainty principle, where this tells you the uncertainty of that measurement. All right, I believe that should be it, guys, and um, that's basically it. And if you guys have any questions, shoot in the comments, email me on my SBU, or whatever email I have in the description. And thanks for listening, guys. Have a good day.